Good morning, BazelCon attendees and you folks out on the internet watching while we're live streaming. So to introduce myself real quick, I'm Long Cao. I'm a staff engineer at Stripe. I work on the build experience team as a tech lead.
And I'm Arie, Luttikhuizen. That's how you pronounce that. And I also work on the build experience team. I've been working at Stripe for about a year now.
Yeah, and I've been at Stripe for about 4 years. As the talk title says, today we're going to be talking about automating dependencies in build files and how we did this with Gazelle at Stripe. So a little bit about the problem we're trying to solve and what this all means. At Stripe we have we have multiple languages in use. We use Bazel to build some of our largest repositories, our users complained about having to manage dependencies in build files. I actually just skipped a slide, but let's go back to it in a sec. Most of you are probably Bazel users or Bazel curious. We know that Bazel requires dependencies to be listed explicitly in your build files. When you do that, it allows Bazel to be very explicit about what actions are being run, the purity about the functions that are being applied, and that gives you cacheability, parallelism, and all these other benefits. But for our users, they find this to be laborious. They complain about this a lot in our user surveys. And as my team was charged to do something about it. And to go back to the slide I awkwardly skipped, this is the team that both Arie and I work on called the Build Experience team. We manage a monorepo with several million lines of code, Java, Scala, Python. We're also responsible for CI performance, things like keeping aggressively low build times. Our median build time, I think, is, 6-7 minutes now?
About that.
Our P95 build time is around 45 minutes. We do use remote build heavily and remote cache. Part of that is not just being CI tuning monkeys. We also look to improve our build tooling and add to the experience such that our users experience a delightful build experience. I know I've used that phrase a lot, but we want to do more than just what's given out in the box. And so this is the project that we've been working on. So when we realized we needed to solve this problem for our users, we looked back and we thought about, okay, what are the requirements that we have? What are the core requirements? Some of these are kind of obvious, but it's worth mentioning just because it did play into our decision to build on Gazelle as a platform. Things like it should be easy to use. It should be fast. For ourselves, we also desired something that could potentially support multiple languages because Stripe is a multi-language company. If you know anything about Stripe, our reputation in the last few years has actually been more on the Ruby side, but we do have a lot of Java, a lot of Scala, a lot of Python for different use cases. Java for RPC services, Scala for data pipelines, machine learning, Python for orchestration code, scripts, machine learning. So these are some of our core baseline requirements. Most people would be pretty reasonable about that. Then we have a laundry list and a long tail of other requirements, things like we want it to be extensible. We want to potentially be able to run this in multiple contexts like continuous integration or remote dev boxes. And we wanted to have features to build on. So when I say things like escape hatches, I mean things like Gazelle directives or configuration. Batteries included was also a super nice thing to have. When we're manipulating build files, what we're doing is manipulating Starlark AST. Personally, I didn't want to have to write my own parser and AST. It sounds like a fun exercise, but having to maintain that in production is something else. So we wanted to choose something that had all this ready.
Yeah, so many of you are probably familiar with Gazelle. I imagine if you work on a Go project, it's pretty ubiquitous. What it is a build file generator. So it'll look through your source code and create build files for you, which is essentially exactly what we were trying to do. Gazelle is great because it provides interfaces so that you can easily extend it for your own languages. And I'll talk a little bit about some of the benefits that led us to choose Gazelle. One being that it's usually fast. It really depends on like what your repo is shaped like and how big it is, but I'll get into that in a bit. Can you go back a sec?
Oh.
Yeah, there's a couple. Yeah, so we're already using Gazelle for some of our Go stuff specifically, which it does out of the box, so it's really nice. And Gazelle's really great because it provides with like these directives you can use, just comments and build files that change the behavior, like if there's an edge case or something. Then yeah, so like I was saying earlier, it's hackable. Like you can extend it how you want, and you can change in your particular extension like how it like resolves things. It does all the file walking for you and like manipulation of build file syntax and stuff that's just a chore to maintain, kind of like what Long was talking about earlier. And pretty recently, a couple months ago, they added functional tests. Like you can just bootstrap easy tests to make sure that Gazelle does exactly what you want. It's really cool.
So, Arie is talking about all the nice things about building on Gazelle as a platform. Of course, it's never that easy. If it was, probably wouldn't be up here talking right now. So we had a few challenges to solve, and this is part of the fun part and part of the difficult part too. So at its baseline, what Gazelle is trying to do for us, or at least the way we viewed it, is how do we resolve dependencies, right? How do we fill in the dependencies attributes for targets and build files? The way we thought about it was how do we map imports, which are basically incoming dependency edges for your code, to dependency targets. If I say import guava dot, I don't know, what's a class, like listenable future or something, how do I know for sure where that came from? And how does Gazelle know that? And how does it fill in the dependencies for the build files? Some other challenges that we have are, this wasn't a clean room implementation. We maintain an old, large repository. The other day, I was curious about how old it actually was, and I think it's a little bit over 10 years. I mean, for a lot of people, that's a lot of legacy. It's a lot of different patterns. There's a whole lot going on, multiple languages, again, as I talked about. And if we want to implement extensions for every language, we then have to do things like parse subsets of the language. We have to know how to handle their third-party dependency ecosystems. So when I say that, I mean things like Java jars that you download from Maven or Python wheels from PyPI.
Yeah, so how did we solve these problems? So how Gazelle works is that at runtime, it'll construct an index of import statements to dependencies that it can add to rules. And that's cool, but it didn't really work for our use case because we had like a really complicated 10-year-old repo that wasn't as simple as Gazelle likes it. And it was slow because it would have to construct this gigantic index whenever it would run. So we came up with two other types of dependency resolution that our extension would use. They both have problems, but we'll talk about how they're complementary. The first is our heuristic-based dependency resolution, essentially because we on the build experience team can control things like lints and pre-commits and stuff like that. We can like enforce the structure of what our repo is going to look like, and then we can use that to make assumptions. And assumptions are really valuable when you're trying to write these things because they're really fast and keep edge cases from leaking in. The other resolutions method that we use is an index-based, which is similar to how Gazelle does it, but we don't create it on runtime. We create like a persistent index on a regular cadence that our tool consumes. So I'm going to talk a little bit about how if you're interested in doing something similar, you can employ like a heuristic-based dependency resolution in your Gazelle extension. And then later along, we'll talk about the indexing. Yeah, so here's a pretty standard one. Is the 1-1-1 rule is a pretty standard heuristic for Gazelle, which is basically you have like one package, in our case, where we're making a Java extension. So it's a Java package. And that's like one package, one directory, one target. Everything is super simple. That's a really nice heuristic to have and rule to have that you enforce, because then you can know exactly which rule in a package is responsible for building anything. And then another nice heuristic is import to path mapping. If you're familiar with Java, you have to define a package at the top of a file, whatever, that your symbols come from. And that package name actually does not have to have any rules to it. Like you could just name it whatever you want. And usually there's like a convention where people will keep that in line with the directory structure where the file is located. But that's not a rule. Like, that doesn't have to happen. So if you don't enforce it, there will always be edge cases. People will get clever. They'll do things that just ruin everything. It's inevitable. So yeah, if you can enforce that, then you get a nice heuristic like this. I don't want to get into it too much, but basically, if a package or an import maps directly into a directory structure, you can know exactly where any symbol is defined, like automatically. Just absolutely takes no time at all, which is fantastic. Yeah, so there's a lot of benefits to the heuristic resolution where it's fast. And as opposed to other types of dependency resolution that, like if you have a daemon or a service or something, it's self-contained. So you don't have to worry if there's like a bug someone's encountering. You don't have to worry about like keeping things in sync, or you don't have to worry about like services going down. You can just pull down their branch, and it should run on your machine the same way it runs on theirs. That's really cool. There's issues with it though, obviously. Accuracy is a big one, where there's always going to be things that break your assumptions. And so that can result in like false positives, or in a rare occasion, you can get like an irrelevant dependency. But to curb those, you want to create rules, which is, I guess, another issue with it, is that you have to create ways of enforcing this. So it's like actually like making lints or whatever. Yeah, it requires some upkeep. And then you also have to maintain it. So like if there's ever any new conventions in your repo, you have to like maintain the tool, which is kind of a drawback.
Cool. So on the other side of the coin, which we believe to be a complementary approach, we also use index-based dependency resolution. What this means is, we build an index of exportable names. Basically the opposite, the way you might call it in the opposite way is things that you can import to dependency targets. And we build this ahead of time, out of band with the tool runtime, out of band with what's going on for the user side. And we build this index, kind of like what your IDE might do when it sees your code. So we do this by way of implementing a Bazel aspect that crawls over our third-party dependency universes and runs an indexing action on it. You can kind of imagine that indexing action to be a function of that takes a class jar, source jar, breaks it open, analyzes the bytecode or parses the code, and extracts exports or importable names. Then the diagram will actually show a simplified version of this pipeline, but then we collate the results together and basically mash together a big index with that's like a lookup table that we can then sideload into our Gazelle extension. As we mentioned, Gazelle extensions are very hackable. They're built with Bazel. You can basically insert libraries that have a execution order, but it allows us to do whatever we want. We can attach metrics. We can load files, and that's kind of the approach we took with indexes. And so Arie kind of hinted at this before, but one nice benefit of index resolution is it's precise, more or less, as long as your indexing code is correct. So hopefully I wrote it well. But what that means really is that when you see an export from a third-party dependency, you have greater confidence that it has a mapping to a target. largely because you can't really use heuristics on third-party dependencies. You can name your names whatever you want in your third-party dependencies. Like I'm not your boss. I don't control you. So we want to be able to say, like, if I import .io.some package or whatever, or .com.stripe. Whatever, like that, we have a way to disambiguate between those. And for the most part, given how we've implemented internally, loaded to a hash map, it's usually a pretty fast lookup. It's nothing where you have to go do database lookups all the time. But the index that I'm talking about here is really on the order of, I think, what was like 5 megs compressed. It's not that large. We've only so far implemented this for Java, JVM dependencies. But we don't anticipate this being a super large or heavyweight process. Now, I've already kind of glossed over this, but like there are issues with index resolution. When I say indexes are generated out of band, that also means there's a potential consistency problem. You may be working with an index that is slightly out of date with your repo at that point in time. And so, I'm mostly going to hand wave this because we actually haven't completely solved this. But like, to be able to summon an index that is completely consistent with the repo, it's not free. Indexing itself is not free. We've implemented this as a Bazel aspect, and so running those actions has a cost. We can either run this on remote builds or with remote execution, or we can run it locally. But there's a compute cost to it, and then that may add extra latency or any sort of like extra steps where something can go wrong for the user. And I already mentioned this, but like when we talk about indexes, we also have to implement them for every single third-party dependency ecosystem. That's just kind of the nature of integrating with more extensions. There's more work to be done.
Yeah, we would use a persistent index like entirely if it were free,
Right.
But that would take 5 minutes every time you run it, which is just not feasible.
I'm looking at the IntelliJ folks I see here in the front row, but we know the issue with like you open your code base in the IDE, it's like you're gonna have to wait for a while because it's trying to do work for you, but you gotta wait.
I wasn't gonna say it.
I didn't mean to call you guys out, but I was just thinking about it.
All right, so I have a little like a dorky little demo that I put together to kind of like show how heuristic dependency resolution method works. This kind of implicitly also does the index-based one because it's using one, but I'm not actually in the demo importing any like third-party dependencies, so you won't see it on display. But yeah.
I have a small Bazel workspace over here that you can check out on the left with one source directory. If I open this source directory, so you have a build.bazel file. In this build.bazel file, there is a custom Gazelle directive that we've written. All this directive does is it maps an import prefix to a directory, main, which we can see on the left. What this means is that any import statement that begins with com.demo, we know it will be under the main directory. All right, so let's enter the main directory. Under here we have two subdirectories, animals and groups. Call them squirrel and turtle. Let's check out squirrel. In here, we see that we just have a single class that extends a base class called mammal. The base classes for this demonstration exist under groups, which we see under here. Now, if we want to build and run this file, we have a build.bazel file here. And in here we have two Java libraries, one for each file, squirrel, turtle, respectively. However, we won't be able to build these because they don't have the dependencies. We have com, demo, groups, mammal here that it won't be able to build that because it doesn't know where it comes from. So in comes build helper. Let's run this here, dev build helper, and I'll pass in the path to the build file that I want to update. If I press enter, these steps should be filled. Excellent. So it does. It adds mammal for squirrel. And if we look into turtle, you can see that it's using reptile. So it does what we expect. That's great. Now let's say for some reason we wanted to import squirrel into turtle. Although there are existing deps in the build file, this should update as we expect. So if I do import com demo animals squirrel and run build helper again, there you go. It's added right there.
Just for a note, build helper is what we call the tool internally.
Yeah, that's our extension. Yeah, so as you can see, that's really fast. And although that was like a tiny, dorky little toy box example, like it is generally that fast on a monorepo with millions of lines of code because it's can make those assumptions about where things are. Going back to the metrics, yeah, let's talk about the metrics of how accurate it is. This is pretty new, so these numbers aren't as good as they will be, and actually they're out of date. Currently, we're a little bit better than this now, but 97% of all of the imports in our gigantic monorepo can be resolved by this and within like a second. Like a file will take a second, not every import, that's a long time. Yeah, so in about 1.5% of build files currently, it adds like a redundant dependency. But yeah, that's pretty much it. It works really well. Yeah, so we originally made this as a CLI tool, but a lot of people just had no idea what it was. It was really hard to get the word out that, hey, you don't actually need to change your dependencies anymore because we have a tool that does that. For one reason or another, that just didn't catch on. So we decided to add a button to IntelliJ. And that was cool because you could just press it and it would just add the dependencies for whatever Java file is open. But even that, people didn't really understand what it did. Like the icon wasn't really, there's no way in like a small icon to say, hey, we'll just add all your dependencies for you in a build file. Like that's, that's a really hard design ask. So we decided to actually integrate it further automatically into our user's edit loop by, in our like internal IntelliJ plugin, listening for whenever an import statement is added to a build file, whether that's through like an autocomplete or when you paste code into a window, IntelliJ will often add the imports for you. So if we can hook into that and then run build helper afterwards, or our Gazelle extension afterwards, then the build file will just stay in sync. So that's soon. I think next week we're going to try to get that in people's hands. Yeah.
Cool. So more or less, we've kind of described the current state of our project. You know, I want to talk about how we think of this as a platform, because we do believe that there's a lot more work to be done, like what things we can be thinking about. Obviously, extending support for all of our other languages, Scala, Python, more support for custom rules that we have in our internal repo. One dream I have personally is just fully automatic generation. You know, if you actually look at how Gazelle works for Go, the happy path is actually fully automated generation, right? Speaking to some Go developers at Stripe, they don't really think about Gazelle all that much because it just kind of works. Like, it does it for them, right? Mm-hmm. We want to get to that point for every other language that we have at Stripe. And then, you know, some of the wackier ideas we've had about this tool is maybe we can run this in CI or different contexts, give users feedback in a different way. We want to be able to put it in front of folks as much as possible. You know, what if we turn into an agent and turned into something that spoke a protocol? If you notice what's going on in the dev tools space recently, there's a lot of like what I like to call protocolization. You know, LSP, BSP. Things that like turn tools into servers and agents, and your clients talk to it. So we have some potential designs around that. We haven't really acted on it just yet. Cool. And you know, if you can go the full length of fully automatic generation, what if you could do stuff like perfect deps, what I call perfect deps, which is you name exactly what your dependencies are, nothing more, nothing less. This is kind of a platonic ideal of Bazel builds, right? You want your graph to be as sculpted as possible so you get the most amount of selectivity. When I make one change, I know that my downstream builds or any sort of dependent targets, those are the only ones that actually get built or retested. And that's kind of the dream, and I think this platform will offer it to us. So I didn't write this down. We didn't write this down on the slides, and I'm sure many of you are wondering if we're ever going to open source this. I gotta disappoint you, and I don't think we're going to, largely because there's a lot of heuristics and just stuff that we built specially for the case that we have, since we're servicing an older repository. Kind of the motivation for this talk, and I hope what you've gotten out of it, is that building upon Gazelle and writing your own extensions is perfectly tenable. Like it's something that I don't think there's a one-size-fits-all for everyone, but it's there and it's available if you have the time, the effort, the know-how, and the will to do so. And from what we found, it's been really, really worth it.
Yeah.
Cool. So thank you for your time. Thank you for listening. Thank you for to the organizers.